Hello everybody, nice to see you all, and happy Thursday to you. Yes, we actually started on time. I decided that if I could, I would like to try to start these things on time, and fortunately today we were able to get all of our equipment back. Welcome to the daily live stream that we have here. Ask Math Anything is the title. And what we do is we answer questions that range all over mathematics, although we kind of choose to talk about questions that I can explain to people who are learning algebra or geometry. So I look forward to seeing what kind of questions you ask today. If you're new to this live stream, welcome. This is going to be different from the usual math classes that you attend, in the sense that this is not something where I have a math lesson ready to teach you. Rather, I'm here to find out what kind of math you're interested in, and we're going to talk about something that you're interested in. So, what shall we do today? I see. I see all of these different talks about different people are asking about things like shirt colors. We're looking to see, is there an interesting math problem to talk about today? Oh, okay. Let's start with that, since that hasn't we haven't said that in a little bit. Time WW Brody asks, how is Novid? Still moving along. I had the fortune of being able to talk to some government people in the last few days. So we're at this moment still waiting for Apple and Google to say yes. But in the meantime, we've continued to build the app out. If you go to the website for novid.org, you'll be able to see there's a video there now, which shows how the app works on both iPhones and on Android devices. So we're still making progress, and finally that last piece is going to be when Apple and Google say, okay. Let's see, what other things can we do here? I'm looking for, oh, interesting. So Daniel Science channel asks a question. How do you calculate pi by only using division? That's an interesting question. I'm not really sure what you mean by only using division, because at some point I might need to also do some addition. But if you ask me about pi, I think what I'd say is that pi actually is just a ratio, right? So if I wanted to calculate pi using only division, if that's the only thing I could do, I think what I would do is I would try to just go and find a really, really big circle, and I would divide its circumference by its diameter. And that's how I would divide. I would just find those two. But let's maybe then talk about the aspects of how you would try to do this carefully. Does anyone know why I would want to find a really, really big circle? Why don't I want to do this just with a little tiny circle? Does anyone know why a big circle is easier? What is the question? The question is, how would you calculate pi if you only could do division? And what I said is, I guess I would go and try to find a really big circle and do division. But why would I want a big Why do I want a big circle? Well, it's in some sense, it's not quite easier to divide in the sense that I'm dividing big numbers by big numbers, but I see that some people are talking about accuracy and ease to measure. And the reason is because, maybe I could put it this way, it's that when we make these things that we're using to measure stuff with, somehow it's hard to be accurate within very, very small amounts in some sense, because my eyes can't even see that small, right? I mean, let me explain it this way. Suppose I was trying to, in fact, measure something like this down to a very, very tight level of precision. Well, then I'd have to move my hands really small in order to even draw the marks on a really tiny ruler. I mean, look at this. I'm going to try to draw some marks with this pen, digital pen. And I can only draw marks that are about that close together before they all look the same to you, before they all look mashed together. So the problem is, I can only put so many marks in a small space. On the other hand, there's not really a limitation to how many marks I can put on a big space, apart from my patience. It's like if I get bored of it, then I guess I get bored of it. But if I just wanted to draw marks at a equal distance, I could do this for a while. So that's why it's easier to do this, if I want a more accurate answer, to do this with a very big circle. Because then I can see that, oh yes, I measured the circumference to the nearest millimeter. I could imagine doing that, by the way. I can imagine measuring with my own eyes something to the nearest millimeter, because I can see a millimeter. But I cannot imagine measuring something with my own eyes to the nearest micrometer, because that's just too small. So that's what I'll do. I'll use division to calculate pi by getting a really big circle. And this also shows how sometimes, like, the scale that you're working at makes a difference. And in this case, if you work at a bigger scale, you get something that's more accurate. Of course, then the next question becomes, where would you get a circle that's this big? That's a little bit harder, but we did mention it on an earlier live stream. What you could do is you could just get a very long string and just stick it to a pole, like get a pole in the middle of the ground, and then just go around with this string. And that's one way to get a nice, perfect circle. More questions. Ooh, Nathan Chen knows what nanometers are. Nanometers are extremely small. Those are like 10 to the power, not they're like, those are 10 to the power minus 9 meters. There are a billion nanometers in a meter. Okay. More questions. Oh, there's picometer. You guys are getting even smaller. Picometer is 10 to the power minus 12, I think. What else do we have? Ooh, that's interesting. Another question about pi. Jerry Chu asks, how do we know pi is real? Like, why not any other number? I'm trying to understand what that question means, but I'm going to say, I think the heart of your question is probably asking, who cares about pi? Like, why not just use some other number instead? And the reason is because circles are really fundamental. Just like how I said, I can draw a huge circle if I want, just with a string. But I cannot easily draw a huge star. It's just not that easy. I would have to do more work. So, and not even just more work, I'm even like, how could I make that super accurate? It would be harder. So the circle is very fundamental, and that's why pi is fundamental too. More questions. Oh, okay. So let's see. I'm trying to understand some of these questions. Ben Tao asks, if you have a certain number of numbers that add up to a certain number, can you calculate the average biggest number? I'm not entirely sure what that means, but I'm going to say the information you gave me was there is a certain number of numbers that add up to a certain number. And that alone is enough to give me the average, right? If I tell you there's 5 numbers that add up to 250, then the average is 250 divided by 5. And the average is 50. And why I said that is because sometimes people talk about averages, and sometimes they talk about, you know, how many numbers are there and what's the biggest. And I saw some other questions about computer programming, and so I'll tie this together with that. Sometimes when you're writing a computer program, you want to keep track of the average number you got so far. You can imagine you're measuring stuff. And suppose you want to know what's the average thing I've measured so far, but every single second you're going to measure something new. What's the best way to do this? You don't need to just keep a list of all the things you've measured and every second recalculate the average. No, what you do instead is you just keep track of 2 numbers. One is, how many numbers have I seen so far? The other is, what's the sum of all the numbers I've seen so far? Every second you get a new number, so you add 1 to how many I've seen so far, and you add that number to the sum so far, and with these 2 things you can always get the average. So I'm just sharing that because someday maybe some of you will write some computer program, and that's the easiest way to keep a running average. What else can we do here? People seem to be talking about a lot of these computer programming things. Tina Jia asked, how many commands have you programmed for Novid? Maybe you mean like how many lines of code have you written? For me, probably at this point, I mean, the ones that I was personally responsible for, maybe several thousand lines. That's not actually that many when you think about the whole program altogether, though. Let's see, what else can we do? Principle of inclusion and exclusion, thanks for asking. The thing is, that's maybe a bit more on the topic of like a standard, that's a topic that you would learn in a class, so I prefer not to hit those. I try to talk about the weird topics. And anyway, that one's actually already in our course. We have a course on combinatorics. What else do we have? I'm trying to see here, you see what I'm trying to do is I'm trying to find some interesting problems that I can say something about, which, you know, maybe is not just like a standard math problem. Okay, Brian Zhang asked, what is infinity factorial? That's interesting. Maybe this one's one that I can say a little bit of something about. Infinity factorial. Well, the problem is that infinity itself is not a number. So I couldn't say it's anything. Infinity is not even anything anyway. But on the other hand, I could say, I think there's a meaning for this. Because when you say infinity, you mean a number that is very, very large and very, very positive. And so that wasn't a number anyway. But if you were going to talk about that kind of a notion, meaning I want something that's huge and positive, then I would probably say infinity factorial would be infinity. And that would be consistent with the way I've been thinking about infinity so far. I mean, consistent with the way I'm dealing with infinity when I write it down. So this is legitimate. What is not legitimate is if I tried to write minus infinity factorial. Well, that's hard to define because you can't take a negative factorial anyway. Now, some people will say there is a way to make factorials for decimals and for negative numbers using something called the gamma function. But at that point, that's not going to have a combinatorial meaning. That's not going to have a combinatorial meaning. You won't be able to have some way of interpreting that. So I'll say there's not really a very useful concept for minus infinity factorial, just because there isn't a very useful concept for normal people for negative factorials anyway. What else can I have here? Yes, somebody did say minus 1 factorial is actually not defined, in the sense that it's not defined for normal calculations, and if you want to use something called the gamma function, you could, but it wouldn't be useful for most of you because you're not calculating with minus 1 factorial anyway. Ooh, that's neat. Philip asks, can every 2D geometry be solved by 3D geometry? That's a deep philosophical question. I would go so far as to say that the answer is yes, because if I have a 2D geometry problem, I could always imagine that I'll use my 3D geometry understanding, and using my 3D geometry understanding, I'll draw this whole thing as a 2D problem, which is in the plane of like a big 3-dimensional space. So, I have this big 3-dimensional space. It might have a sphere. I don't know if this thing makes any sense. I don't know if you can see this. But if I had a problem that was about a circle in 2-dimensional space, I could imagine that was just part of a 3-dimensional space, part of a sphere, and I took a cross-section. I just cut through it. So actually, every question that's about 2D, you could actually understand by trying to think in 3D and putting it inside. But why I like your question is because the other direction's not true. Like somehow, if I want to understand 3D, and the only thing I happen to understand is 2D, it's a lot harder to go and say, you take 3D and you put it in 2D. We know this because whenever we try to draw in art class, or even like now on my diagram, when I'm trying to draw a 3-dimensional figure on a 2-dimensional board, it's actually quite hard. So in some sense, if you happen to have more dimensions, you can do more stuff. Maybe that's why we're able to be more powerful than ants. We understand 3 dimensions. Ants probably only understand 2 dimensions. But, maybe there's some aliens out there who can understand 4 dimensions or something like that. And then they would be more powerful than us in being able to conceptualize more things. Actually, it's quite fun to go up a dimension. One of the first research projects I ever did when I was a college student, the key to solving it was to go up a dimension. It was basically that we were doing some problem. You could almost think of the problem as on a plane. And by taking one step out, you were able to realize that the problem was actually a 3-dimensional problem. Okay. More questions. Somebody said Skylar is saying the 4th dimension is time. That's often what we use. When we use space and time, then we think of time as the 4th dimension. Batmobile. Nice name. You asked, do I believe in aliens? I'm not entirely sure, but I'll say I think it's very dangerous to say you definitely don't believe in aliens. If you assign a probability of 0 for aliens to exist, that's a dangerous situation. Somehow 0 is a very strong statement. So the way I am is I just live my life. I look at facts. I'm a scientist. And I go based on what I've observed. And so far, aliens haven't changed my life significantly yet. If that were to be likely to change, I might adjust quickly. But right now, I don't know about those UFOs. If you're asking about those UFO sightings, I'm not yet sure I know what those are. Also, as you may know, sometimes people observe things that turn out to just be mistakes when they were observing. There were a few years ago, some people thought they had ran a physics experiment and something moved faster than the speed of light, which would contradict some of the fundamental theories of physics. And indeed, afterwards, it was found out that it was a measurement error. But still, this is just showing that somehow, when something goes so far against your theories, the first thing you should check is whether or not those things are just, maybe measured wrong in the first place. Okay, what else do we have here? Okay, this is a cute question. I'm just trying to understand what this question means. So Joshua Wu says, suppose that 20%, I need to write the whole question down and stare at it. 20% of a number is 17. Find 20% of 17% of the number. 20% of 17% of the number. So I just chose that. I chose this question because I think it's cute for a few reasons. The first is that it's got a lot of these like percents in it, and I just want to know what the answer is. And the second thing is I bet that this was in the year 2017. I bet that this particular problem was from some contest in the year 2017 because it has 20 and 17. Some people said they can't read what I wrote. It just says 20% of a number is 17. Find 20% of 17% of the number. Okay, so how would you do this? Well, whenever I have something like this, the first thing I try to do is try to translate the problem into some words. So I don't know what the number is. I guess I should call the number x. So if the number is x, then what I know is that 20% of x is 17. That means that 0.2, I'm going to use decimals because it looks convenient for decimals. 0.2 times x is equal to 17. And what I need to figure out is, what is 20% of 17% of the number? Oh, I see already what's going on. I want 20% of 17% of the number. Now, once you write this down, or once you interpret it, you see, oh, actually, I don't even need to know what x is, because I have 0.2x over there, and I have another 0.2x over here, right? This is 0.2x times 0.17. So I'll just take the 0.17 times the 0.2x, and that's equal to 0.17 times 17. And 17 squared is 289. If you do enough problems, you see it. And I have a point. It's like 0.17, so I should move 2 decimal points over, 2.89. Okay, that was cute. And afterwards, when I look at this particular question, I would say, I see how you could have done it fast. The way you do it fast is you say, you already know that 20% of the number is 17. And so this 20% of the number is that 17, and I want 17% of it. Okay, cute. Thank you for sharing. What else can I have here? Since we were talking a lot about dimensions, Andrew Chow asked, can something be one dimension? Yes, it can. One way that you can have something which is sort of one-dimensional is if you have things that are moving on a long line. Actually, you could think of that as time. Like time itself is only one dimension. There's only forward and backwards. Another thing that you could imagine that's one-dimensional is if you happen to have some very long train track. If you have a very long train track and you're just imagining the train moving on the track, even though it's moving in three-dimensional space, really what's going on is you can tell where the train is just by how many miles away it is from like New York or something like that, if the track is from New York to Los Angeles. And the idea of one dimension is you only need one number to represent where a point is. And so if you have a long train track, you just have to say how far away is it from the start of that train track. So it's actually quite useful to think about dimensions this way. Dimensions, the number of dimensions is really how many different numbers do you need in order to express where you are. And in that sense, that's why you say that the surface of the Earth is two-dimensional. What are the two numbers we use to describe where you are on the surface of the Earth? Does anyone know? You guys probably know. We've talked about this one before. If I have a point on the Earth, how would I describe where it is? I would give two numbers, latitude and longitude. Thank you very much. You're very, very quick. And so that's how I would describe a point on the Earth. And in general, you just think, how many numbers do I need in order to describe that point? And that'll tell you roughly how many dimensions there are. Okay, more questions. Hi Lan Fan asked, how long would Bumblebee take to travel around the world? Now, this is a fun question. Traveling around the world. Does anyone know what's the fastest way to travel around the world? There's some book, I don't know if you've read this before. It's called Around the World in 80 Days. It's a really interesting book. Does anyone know the fastest way to travel around the world? Flying, plane? It's pretty good. How long does it take? What do you think? How long does it take to travel around the world by an airplane? Aha! David Tiang already got it. So the way you do it is walking. You don't need a plane at all. The plane's too hard. You just go to the North Pole. See, here's the North Pole. You just go to the North Pole, and obviously the North Pole is a pole sticking in the ground, right? No, it's not. But anyway, some people like that in cartoons. In any case, you go to the North Pole, and you just kind of go around the North Pole. Boom! You went around the world. That's cheating. I mean, not that that's cheating, but that's something that's kind of funny. It's like, what does it mean anyway to go around the world, right? What does it mean to go around the world? Actually, that does count as around the world. If the way we often think of our world is there's an axis that the Earth is spinning around. And so you can go around the world very quickly. If you're a bumblebee, you just have to be a bumblebee that can handle cold. And if you can handle cold, you can go up to the North Pole and buzz around one loop, and you've gone around the world. Now, if you actually want to go around the equator, that would be a different story, right? So if the question became, how long does it take to go around the equator? Now you need to use the circumference of the radius of the Earth, the circumference of the Earth, the speed of flight, and so on. We did something like that on an earlier live stream, so I won't do it again. But I wanted to bring this up just to say there's this funny idea of what does it mean to go around the world, right? And actually, when you think about it, a lot of times when you are flying around the world, if you fly around the world, you can sort of count how many times you've gone around the world based on how many times you go around that North Pole. So that's actually a way of thinking of this. And this is the beginning of a concept called a winding number that people would see sometime later if you're studying college math. Okay, what else can we do here? Looking at the questions. Okay. Somebody says that they live in Southern California and it's pretty cloudy right now. It's really interesting to be able to have this live stream to touch all these different climates and parts of the country and the world. Oh, okay. So this is interesting. I see a riddle. This is a riddle that looks like fun because I don't know the answer. And maybe all of you can help us figure this out. Eric Feng writes a riddle. And I'm just kind of curious. I like riddles. The riddle says, there are 3 switches. 3 switches outside the attic. Okay, so I guess there are 3 switches outside the attic. What do switches look like? They look like this. I don't know if this looks like switches to you, but this is switches now. Okay, we got 3 switches here. And you may flip the switches and then make one trip to the attic. Okay. Match each light with its switch. What? I don't quite understand your problem, but anyway, let's see. There are 3 switches outside the attic. Presumably that means there are 3 lights in the attic. And the question becomes, you can flip the switches and then you can go to the attic once. You can go to the attic to look. And the goal is to find out which switch is for which light. Okay, that sounds kind of cute. Let's see. Does anyone understand this particular problem? First of all, let's think of this together. This sounds kind of interesting. We've got this 3 switches outside the attic. And in fact, this is something that happens in a normal house. You see these switches. Actually, our attic has 3 switches too. So somebody says, get a second person with the switches, right? I'm just trying to think what would you do in this problem, right? I know that it's a riddle. Riddle usually means there's some super clever solution. But what might we try to do if we were just trying to solve this problem in real life? There's 3 switches, and there's 3 lights up there, and I get to flip some switches, and I need to figure out which switch makes which light. You hate riddles? Oh, come on, riddles are fun. That's why I picked this one, because I don't know the answer either. Well, let's see. So right now, let's assume that all the lights are off. Are we going to start with that? Or we're going to start by assuming that all the lights are off. Let's do that. That makes a simpler problem to begin with. Yes, so Sultan says you don't quite get it. I don't quite get it either. And that's why what I'm doing with this is I'm not just playing a riddle problem. I'm just talking about the real life, right? If in real life you saw in your house that the attic has all its lights off and you see these 3 switches here, how would you figure out which switch is which? I mean, there's one way to do it that I could figure out. And one way to do it involves checking 3 times. Does anyone know what that is? There's one way to do this. Yeah, let's assume that the lights start out off. Thank you very much, Eric Feng. That makes life easier. And 3 lights in attic, all are off. Okay? So then the question is, what should you do? Well, if you can see, if you're looking at this problem, if they all start off, I guess I could try to turn one of the switches on, and if I turn one of the switches on, then I'll find out which light that is. And that will take me one trip, right? Does that make sense? So does it mean that that's the only thing I can do? Is the only thing I can do to turn one switch on, look at whether the light turned on, come back down, and then turn the second one on. And if I turn the second switch on, I go back up, and I'll find out what the second light was. And guess what? I don't need to go a third time because the third light is the third one. Does that make sense to people? So what I'm saying here is that I see how I can do this in 2 trips already. The first trip is just flick the first switch, run upstairs and take a look. Okay, now I know which light that is. Come downstairs, flick the second switch, leaving the first one on, go upstairs and say, oh, okay, now I know what the second one is because that's the new light that's on. And I also know the third one because that's what's left. So I see that I can do this in 2 trips. But Eric Feng says you must make only 1 trip. Does anyone have any good ideas here? If you can only make 1 trip, what could you do? Actually, I'm curious too. That's why I'm asking everyone. What are we doing? We're trying to figure out what to do. What we're doing is we're saying that there's these 3 switches and they can turn, each of them turns 1 light on in the attic. And so far we've figured out how we can do this in 2 trips to go and figure out which switch is which. But now, how would we try to figure this out if we can only make 1 trip? This seems a little mysterious to me, to be perfectly honest, because somehow it seems like, yeah, I see there's a bunch of different questions here. Some people are suggesting things like blowing up the wall. I assume that's probably not the best solution here. Some people are saying, you could try to figure out what happens if you turn on a switch and then turn it off and the light bulb is hot. Actually, that's a pretty good one. That's a pretty good one. I like that. I like that. Yeah, I like that. Let's do it this way, okay? What if what we do is we just turn on one of the switches and turn on a second switch, okay? Turn on 2 of the switches, and I'll have these 2 switches on, and then I'll wait for, 10 minutes. And then I'll turn off one of those 2 switches. Great. Now I go up and check. And one of those lights is on, one of those lights is hot, and the other light is off. Is that the right answer? I see that that's what you guys were saying. So you guys are pretty good. Actually, you guys are pretty clever. Actually, Eric Feng, what is the answer? Is that the correct answer, Eric Feng? Probably. It seems like people generally like this idea. And Eric Feng says, yes, that's the answer. Spectra TTV says, oh, but maybe they're LED bulbs. Well, you see, even LED bulbs get warm. I'm curious. Let me double check. One of my lights here in this studio is an LED bulb. Let me check. Yes, they get warm. They get warm. So I just went and touched an LED bulb. I didn't die. I'm still here. Oh, please do not touch your light bulbs at home. This is not recommended. I'm not here to recommend any dangerous behavior. Please do not touch light bulbs at home. Okay, thank you. Right. In any case, I think we've solved the problem. Thank you very much, Eric Feng, for sharing this interesting riddle. And I will also say, I'm really impressed by all of you people here. You guys are pretty clever. Okay. What else can I do? Oh, by the way, No Name is saying, yes, light bulbs are really hot after 1 hour. I think the relevant thing here is it depends on what kind of light bulb. If you have a light bulb, which is the old-fashioned kind, those actually get really hot. Don't touch those. Yeah, you're right. Why did I touch it then? Well, I got close. I didn't actually touch the bulb exactly. The reason I dared to get close is because in this studio, our LED bulbs are protected by there's like another plastic in front. And so I just touched the plastic in front, and I could tell that from the plastic in front being warm, that means that the bulb behind it was actually warm. LED bulbs aren't too hot, you're right, but they actually do get warm, especially if they're bright. So anyway, there's a whole topic around LED bulbs, which is very, very interesting too. All right, let's see. Let's talk about some more questions here. Ooh. Panda Ruby asks, how do you make sure you don't waste time? That's a good question, I think the main thing is to understand about what it means to use time, right? It's when you see time as a resource, when you have some goals. I guess that's mainly the thing. It's like when you have some goals of things you want to do, then you're just really occupied by trying to make sure you can do those goals. And then you don't want to waste time because it's just like, if I waste time, I will get those goals slower. So I think the main thing is just to get a purpose in life, right? To go and say, I have a few things I really want to do that I believe in. And then you'll find yourself organizing your day to make sure that you can do those things. More questions. Yes, yeah, Panda Ruby. Thanks for your comment. Also, I mean, I really do think something that happens a lot is if you don't have your own goals, like if your goals were set by someone else, or if you don't really know why you're doing them, then it's like life is pretty boring. But after a while, it's actually more interesting if you can just figure out what you want to do, and maybe not like what you want to do because you enjoy doing it. It's like, why am I here? What am I trying to achieve? Right? And in some sense, you can see what I try to do. What I'm trying to do is to make it so that there's some positive impact on the world. What else can we do here? Woo. Andrew Chow, this is a neat question. You asked, what is the most uncommon sequence? To me, I think the way I'd answer this question is it has something to do with what things are structured and what things are random. You see, if I gave you a sequence, and the sequence was something like this. Here, I have a very special sequence. This sequence goes 1, 1, 1, 1, 1, 1, 1. This sequence is boring. It's just a whole bunch of ones. Okay, so you'd say this is somehow, I've seen this sequence before, or it seems to make sense. The sequence makes sense, and so it's not that special. It's actually more common than you'd have expected, right? 1, 1, 1, 1, 1. That's a very common sequence. What if I write another sequence? I have another sequence for you. This sequence is 1, 2, 3, 4, 5, 6. Okay, that's still boring, but maybe a little bit less boring, right? You can barely see that. This is interesting. So I'm a little bit curious if somehow the way that our graphics are today are dimmer than usual. But in any case, like less boring, right? It's still boring, but less boring. But unfortunately, all of these things are things that have patterns or they have meanings in them. Here's one that's better. 1, 2, 1, 2, 1, 2. Oops, that's a weird 2. Not much better, but it's still getting more, like it's somehow now it's repeating with 2 things, right? And maybe let's make another one. Let's make another one. Here's a sequence. 3, 1, 4, 1, 5. Oops. 5, 9, 2, 6. Well, actually, even though this sequence is something that some people have seen before, I mean, even though the sequence seems a little bit weird, it's still a sequence that you've seen before. You can say where it came from. So my point is, anything that you can sort of see where it came from, or anything that has a pattern, to me, those are all common. The things that are uncommon are things that have no pattern whatsoever. The only problem is, those are really hard to make. And that's actually why they are uncommon. How would you make a random sequence anyway? It's not even clear to me that my brain is a good random number generator. You know, it's not clear to me that I can make random numbers. In fact, there's a fun experiment where if you tell people, randomly make up the results of coin tosses, like randomly go and make up heads, tails, 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 heads, heads, tails, make a sequence. If somebody does this and you try to make a heads, tails random sequence without actually flipping a coin, and you make 100 of these things, most of the time, you can figure out that it was made by a human and not made by actually flipping coins. It's because somehow we're actually very bad at making random things. So my answer to you about what's the most uncommon sequence is, it's the sequence you get by really randomly generating things. For example, I can make such a weird sequence by grabbing a coin and flipping the coin and writing a 1 whenever I get a heads and a 0 whenever I get a tails. And what I get is going to be an extremely uncommon sequence. As I keep flipping like 100 times, 1,000 times, that will make a sequence. Actually, if you flip it, if you flip that coin like 10,000 times, I guarantee you will get a sequence that nobody in the world has ever seen before. You know why? It's because if you make a 0-1 sequence, which is just made by flipping coins and getting a 1 if it's a heads and a 0 if it's a tails, if you do this 10,000 times, the probability that somebody else matches your sequence is 1 over 2 to the power 10,000. And that's just enormously huge denominator, which is an enormously small probability. So that's how I would make an uncommon sequence, from randomness. Okay, what else can I do? Or scrambling cards, you're right. If you scramble cards, you're also going to get something very random. Someone's asking about the pure tone generator. Please do not play it into your headphones. I've learned my lesson. So you've all learned some things from this live stream. Don't play the pure tone generator into your headphones, and don't touch light bulbs. What else can we do? Oh, neat. Andrew Chow asked a probability question. What's the probability of flipping 10 coins and half of them are tails and the other half of them are heads? We can do this exactly. So Andrew Chow wants to know, what's the probability of 5 heads and 5 tails in some order if you flip 10 times? Okay, that's a legitimate question that you might want to ask. So the way you do this is you'd say it's probably going to be more likely than we expected. It's one of the most likely outcomes. It's half and half. But the way you do this is you say, well, probability is how many of the outcomes are good divided by how many outcomes are there altogether. You see, because when I say outcomes, it's like I've got 10 times that I either have a head or a tail. So I'll have a sequence of 10 things. Each of them is either a head or a tail. So the number of possible outcomes is equal to the number of ways I can write 10 H's or T's. It's actually 2 times 2 times 2 times 2, where I have 10 of these. And again, that's because I'm flipping 10 times, and each time it's either going to be a heads or a tail. Does that make sense to people? It's like I have heads or tails, heads or tails, heads or tails. I make one of these decisions, and I make the decisions 10 times. So 2 times 2 times 2 times 2, like 10 times. Okay, that happens to be 2 to the power 10. But we also then need to find out how many of those sequences are good. How many ways can I have like 10 things, and 5 of them are H's and 5 of them are T's? That's a certain way of finding out how many ways there are to rearrange 5 H's and 5 T's. So the number of good outcomes is equal to the number of ways to arrange 5 heads and 5 T's. Okay, so I want to know how many ways that I can rearrange all of this. Well, if I want to rearrange this, the easiest way to solve this is to say that's actually the number of ways out of, well, no, let me explain it this way. I've got 10 things, and we've been talking about factorials before. If you want to rearrange 10 things, the number of ways is 10 factorial. It's like 10 ways to decide what goes first, 9 ways to pick which of the other ones comes second, 8 ways to pick which of the other ones comes third, and so on. And so the number of rearrangements of 10 things, number of arrangements of 10 things is equal to 10 factorial. 10 times 9 times 8 times 7 all the way to times 1. So clearly the answer is 10 factorial divided by 2 to the 10, right? I'm done. Well, no. The problem is that that's kind of big. 10 factorial is huge. 2 to the 10 is not as huge. Actually, 10 factorial is like 1 times 2 times 3 times 4 all the way to times 10. 2 to the power 10 is just 2 times 2 times 2. More boring. Just 10 2's. This is 10 numbers, some of which get huge. So you can't just take 10 factorial over 2 to the 10 because some of these rearrangements are the same. So actually what you do, and what we talk about in the combinatorics course, is that if you want to know how many ways there are to rearrange 5 H's and 5 T's, where I can't tell the H's apart and where I can't tell the T's apart, is you take the 10 factorial and you need to then divide it by the number of ways to rearrange the H's amongst themselves and the number of ways to rearrange the T's amongst themselves. Right? It's not just 10 factorial because these are not distinct H's and distinct T's. They all look the same. So in fact, what I need to do is I need to say the number of arrangements of 10 things if 5 are same and other 5 are same. Let's write this a little bit more clearly. Other 5 are same. That's equal to 10 factorial divided by 5 factorial, 5 factorial. So now I need to calculate this. 10 choose 5, is that right? Shireen Zhang, that is right. So yes, you just need to go and calculate this part out. This is also the same thing as the number of ways from 10 positions to choose which 5 of them are h's. Yay! Okay, I'm glad you're happy. So now what is 10 factorial over 5 factorial? 5 factorial is just like, let's try to divide this thing. What is it? So this is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 5 times 4 times 3 times 2 times 1. That's 5 factorial. Oh, look at that. 5 times 4 times 3 times 2 times 1. They match. That's nice. That matches that. So they cancel. So that part cancels. And so now I just need to go and simplify out this piece. What is that? 10 times 9 times 8 times 7 times 6. Let's go and do some canceling. It's a canceling party. 5 and a 2 cancel with a 10. Okay. What else can I cancel? Oh, okay. The 4 is going to cancel out with the 8 and leave me a 2. Let's write the 2 more legibly. The 3 cancels out with the 9, leaves a 3. We're almost done. I just need to know what is, anyone can help me? 3 times 2 times 7 times 6. What's the easiest way to do that? 3 times 2 is 6. I need to do 6 times 7 times 6. 6 times 7 is 42. Now I need to do 42 times 6. Oh, wait. There's a lesson. Don't multiply all these out yet. I'm supposed to divide them too, right? I'm supposed to take the 3 times 2 times 7 times 6 and then divide it by 2 to the power 10. Maybe I can do more canceling first. That's an important note. Always do all your canceling before you do any multiplication. So let's write that on the next. Do we need a next screen? No, we can write it up here. So the answer is 3 times 2 times 7 times 6 divided by 2 to the power 10. If I have 2 to the power 10, now we start doing more canceling. The 2 cancels away a 2, so the 10 becomes a 9. I don't know if this is a nice way to do it, but I hope you understand what I mean. The 10 became a 9 because I canceled away a 2. Next thing that happens, the 6 is going to cancel away a 2, leaving behind a 3. And when I take away a 2, I get an 8. Okay? I think we have an answer now. So the answer is just going to be 3 times 7 times 3. I can do that. 3 times 3 is 9. 9 times 7 is 63. And what's left is 2 to the power 8, 256. Here's your answer. Now I want to take that answer and think about what it means. 63 over 256. I want to go and check if that makes sense. How big is that? Well, to me, 256 is 4 times 64. So this is approximately 1/4. Maybe that seems reasonable. If I go and flip a coin 10 times, the chance that I get exactly half heads and half tails is about 1/4 of the time. And that seems quite reasonable. So there's your answer for you. Okay. What else can we do here? Oh, you guys are so funny. All right, somebody said, here's a riddle, okay? Pepsi. These are fun riddles, but this is not really a math riddle, but it's okay. It's a logic problem. I have to write it down for you, and you have to put up with my bad handwriting. But I'm gonna write it down for you because then we can all stare at it together. Riddle by Pepsi. It is David's parents have 3 sons. Snap, crackle, and what's the name of the 3rd son? Anyone know? Oh, you guys are so quick. Yes, the answer is David. Okay, well done. So the answer is David. It's not Pop. So, okay. In any case, these are all these funny things. Like, it's a logic puzzle, but it shows that when you read something, you should read it very carefully. More questions. What do we have here? Batmobile has another question. You have a fun username also. Batmobile asks, what are good books for AIME preparation? The AIME preparation. So this is the AIME, the American Invitational Math Exam, which is a contest that many people can take, definitely at high school and maybe earlier. And if you want to prepare for the AIME, to be perfectly honest, I'm not entirely sure you need a book. I actually feel that the books are fine, but you can get a long way by yourself messing with the problems. So I would actually recommend play with the problems. In some sense, what you want to do is you want to learn how to attack a question by first fighting with it a bit, struggling with it, and then seeing how the question is done. So I have a very weird way of learning. My weird way of learning is to say, I'll always want to go and attack questions that are not too hard for me, but still challenging. And when I can't do them, read the solution. And when you read the solution, you learn a new technique. But half the time, you actually also figure it out on your own first. So that's my answer. Actually go and try questions. Just like how on this live stream, right? Sometimes a question comes in and it's like, I want to know what it is. Let's try. And then usually what happens is you guys all save me. What else can I do? Somebody asked about the hockey stick identity. That's something where you add up a lot of numbers in Pascal's triangle and you get another one. I'll just give that to you as a, try that for yourself and you'll find something interesting. Add a bunch of numbers on the Pascal's triangle along a diagonal and you'll see something. Start from the edge. Okay. Oh, okay, so here's a question. Somebody asked how to make sure that you can be consistent with your grades even though the questions are hard and you still spend lots of time on it, need lots of help. Here's what I'd say. Anything that seems hard, you should know it's not going to be too hard for you. There are very few things in the world that are really too hard for you. Usually what it means if something seems hard is that maybe the way that you're attacking it is not quite right. So here's a general advice. If I see something and I'm like, well, it looks like a lot of people in the world can do such a thing. Why is it hard for me? Number one, find out what they're doing. Actually, it's very, very effective technique. You see other people are able to do it. You figure out, what do they eat? Do they eat some really strange things? The answer is no. Then you ask, do they have any strange behaviors that give them an advantage? The answer is usually also no. Then what it turns out being is that, they must have a better strategy. So then what you want to do is you want to learn from the strategies, right? So if you happen to have any friends who are having good grades, you sort of ask them, how are you doing it? What's the secret? What do you need to do in order to make all of these things work? Sometimes you're not so lucky. Sometimes there's no one around you who you can ask. And the best example for this is if you're preparing for the Amy or something like that. If you're preparing for really hard things, there's no one near you anyway. And then so what you need to do if you want to find a way to crack through the hard stuff is to keep trying new strategies. Actually, this is how I lead my life. I try to do hard things, and I constantly keep coming up with new ways to say, can I try this approach? Does this approach work? Does this approach work? And if you just keep coming up with new approaches, eventually one of them works. Unless the problem that you're trying to do is so hard that no one in the world can do it. And that's not going to be the case with your grades. So usually my answer I'd give to that is, it's probably that the way that you're trying to do it is maybe not the most efficient. And you want to, early in your strategy, figure out what is the most efficient way, because otherwise you can waste lots and lots and lots of time on an inefficient strategy, only to find out that in the end, it didn't work. I think the answer is called be strategic. Hard work is important, but so is strategy. And keep thinking of that. Okay, more questions. Oh, this is neat. Here's a question that's pretty deep. Mohammed Guelan asks, why are zeros of functions interesting to study? So why would anyone care where functions are zero? So there's a reason for this. This gets a little bit more advanced, but it's still really Algebra 1. Hey, I have a parabola for you. I have a parabola. A parabola just means that I have a graph. And the graph is a graph of a quadratic function. It's a function which has an x squared inside it. And this parabola, it kind of goes through, look at that. It does this. And I'll tell you something. Over here, here's what happened. This occasionally happens. When this happens, what I do is I need to quit this piece, and reopen it. Oops. Just a second. What? Where'd it go? Now you're seeing how I do everything. That ought to work. Okay. People are asking what I'm using. So I'm using Linux. This is something very powerful, and the Linux lets you go and what you just saw me do is you saw me kill a process. What that means is like whenever anything looks like it crashed, you can actually just force it to go away. So what you were just watching is that I'm using an operating system called Linux. It's not Ubuntu. It's actually running something called Debian, which is which is actually what Ubuntu is based on. But it's very stable in the sense that whenever anything happens to crash, you're able to just go in and close that piece that was crashed immediately and then reopen what you actually want. Why use Linux, Eric Cho asks? It's because it's actually more powerful. For what I'm trying to do here, the fact that, something crashed. I mean, how often does your computer crash? It crashes. And what you saw is it crashed, and I was basically like, get rid of that one thing that crashed. Boop. And then as soon as it's gone, come back. Okay, but let's continue. So what was that question that we were just talking about? We just got sidetracked. Actually, someone needs to remind me, where were we? Oh yeah, zeros. We were talking about zeros. That's right, let's talk about zeros, because that's neat. There's a parabola here. And this parabola looks like a smile. Over here it's -1. Over here it looks like 2. Great. If I tell you that, you can already say a lot about the parabola. Oh, Aaron Peng says, Debbie, I thought he said the Linux ran something called Debbie. No, this Linux is called Debian, Debian. And I seem to remember the reason it's called Debian Linux is because the guy who did it, I think he might have known a Debbie or something, and his name was Ian. I'm not really sure. Somebody can look this up later. But about zeros, why do you care about zeros? Look, here's a parabola. And if I tell you there's a -1 and there's a 2, it turns out that there's a way to write down the equation of this parabola. This parabola, at this point, because there's a -1 and a 2, it's a function. The parabola is like a y equals something, right? It's like a y equals, and it's got some x squared stuff, right? It's like something x squared. That's not an m, that's just like weird squiggle. Plus something x plus something, right? That's a parabola. But what's useful about this is that it turns out that you can write it down in a factored form. It's because you see this parabola equals 0 at -1 and at 2. So if you remember how you can solve quadratic equations, when you want to solve a quadratic equation, you want to solve like an x squared, something x squared plus something x plus something equals 0. And in particular, the fact that there are 2 roots already here, that tells me that actually this parabola is something times x minus -1, which is x plus 1, times x minus 2. Did that make sense? This is very powerful. If I just draw you a parabola and I go and get the 2 zeros of it, the places where it's 0, then I can actually write down the parabola as it's just something times x plus 1 times x minus 2. And this in fact works even if you have like a higher degree polynomial, if it's like a cubic polynomial or a quartic polynomial. If you happen to know where the roots are, you can actually write down x minus the root, x minus the root, x minus the root, do all of these, and then you just have one number in front. And that's why this is powerful. Okay, more questions. Well, maybe I want to say one more piece about this. This shows how the roots basically characterize what your polynomial is. There's only one degree of freedom left, only one thing left that you can mess around with. And that thing you mess around with basically says how big the amplitude of this is. If I go and change this number to 10 times the number, what that would do to this parabola is that it would actually just stretch it. Maybe that wasn't 10 times. Actually, maybe that was 10 times. But I'm just trying to indicate that the way that if you change the number in front, you just kind of make it stretch like this. Okay, more questions. Oh, neat. Anonymous Cheetah asks, how advanced is Evan Chen's EGMO? So there is going to be EGMO. You were talking about a book, I think. There's a book called Euclidean Geometry and Mathematics Olympiads, EGMO, written by Evan Chen, who is a person who helps us with coaching the US Math Olympiad team. It's a really good book. How advanced is it? Well, it's worth knowing that he wrote it when he was in high school. He actually wrote it in his last year of high school. And so it's sort of showing insights on solving Euclidean geometry, like solving your geometry problems for Math Olympiads from the point of view of a really, really good high school student. Where really, really good is like really, 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 really good. Okay, more questions. Whoa, here's something I didn't know. George C. says, question, why, if a straight line passes through the curve y equals x squared, the two interceptions, oh, I do know this. This is neat. Okay, this is neat. Let's do this. So this is something which is saying, look, here's y equals x squared. Oh, here's a tip. I want to graph y equals x squared. I was about to draw the axes. Don't start by drawing the axes. Start by drawing the parabola itself. This is a cheat, but a very, very useful cheat if you're teaching math. Now that I've drawn the parabola, that's y equals x squared. Now I can go and draw the axes. See, look how this is so much easier. That didn't look quite right. Try again. Close enough. But you see, you can see if I first started by drawing the axes, as I came down with the parabola, I would probably be like, oh no, it's not getting to this place right, and then it's over. Draw the parabola first. Okay, now that I've gotten this, you have something interesting. You said, let's just draw a straight line. And in particular, here's what you wanted to do. You wanted to say, look, let's grab some number here. Like, let's pretend we're at 2 here, and it goes up to 4. So this point here, sorry, not 2, -2. This is -2 and 4. Okay? Let's do the same over on the other side with 3. 3 and 9. This is 3, and this point is 3 and 9. All right, everyone, let's go and try to figure out, let's go and try to figure out what is the equation of this line. Can you help me with that? What's the equation of that line? How would you find the equation of a line through 2 points? Do you guys know good ways to do this? This is an Algebra 1 topic. I have 2 points, -2, 4, and 3, 9. And I want to know the equation of a line that goes through them. What kind of methods do we have? If I have 2 points, point-slope form is a pretty good idea, all right? So let's use the point-slope form. And if there are any teachers watching this, I think this is a really neat topic to talk about when you're learning about just drawing line between 2 points, because it makes a neat coincidence. Okay, this is a very interesting problem to do because it looks just like any old problem you'd have to do. I've got a point, I've got another point. Let's just find the equation of the line through them. How do you use point-slope form? We need the slope. Well, what's the slope? The slope is the change in y, which is 9 minus 4, divided by the change in x, which is 3 minus -2. Yikes, it's a ugly number, right? Wait, no, it's not. It's not an ugly number at all. This is a really nice number. It looks like it's 1. I got lucky. Okay, it's 1. I like it. It's 1. Okay, now if I want to use point-slope form, let's just go and find a point. How about the 3, 9? Point-slope form with that point 3, 9. The way that works is actually this is how I remember point-slope form. I say that whatever the y and the x are, y minus one of the y's, which is 9, over x minus the x has to be the slope. Because that's actually how I think about this. I'm saying I've got a point xy, I don't know where it is, but wherever it is, it needs to satisfy the slope. If I had an xy somewhere, then the difference in the y's, y minus the 9, divided by the difference in the x's, x minus the 3, that better be 1. That gives me an equation. Y minus 9 equals x minus 3, and so y equals x plus 6. Now that's slope-intercept form. Once I have slope-intercept form, that tells me where this is. This is at 6. It's at 0, 6. And what the person asking the question was saying was, look, 2 times 3 is 6. That's neat. Oh, somebody says when x equals 3, it doesn't work. You're right. You're right. So this particular thing is not quite right. That's why I wrote the next line. The next line is the point-slope form. So what I wrote here was how I'm knowing how to get the point-slope form. In fact, this thing here is true only when x is not 3. That's true when x is not 3. Okay, thanks. That's a very important detail. But then I get something here which is true for all x's except 3. And since it's a line anyway, I may as well just put in that point at x equals 3 as well. But now the interesting thing here is, I have just found out that the intersection is 6. And 6 is 2 times 3. That's a neat Coincidence. Just a coincidence, right? Well, of course not. Let's go and try to show how this works in general. The way to show how this works in general is just to not use numbers like 2 and 3. Let's erase the numbers. Instead, what we'll put are variables. So maybe on this side I have minus a. And if it's at minus a, then it's at minus a, comma a squared. Now if I go and look at this one, if I'm at b, this is at b and b squared. So now what do? I just go and look at what I have here and adjust. Okay, so it's not 9 minus 4 over this thing. Let's go and write down what it actually is. And it's not equal to 1 either. The slope is going to be the change in y, which is b squared minus a squared, divided by the change in x. And the change in x is b minus negative a. That's actually b plus a. This is good. This divides nicely. b minus a. Let's do a quick check. When we had b is 3 and a is 2, 3 minus 2 was 1, it works. Okay? Now we go and write this piece. It's not y minus 9, it's y minus b squared, x minus b, and it's not equal to 1, it's equal to b minus a, and not when x equals 3, not when x not equal 3, it's when x not equal b. As you can see, I'm just using my original numbers and substituting in things that I don't know. Wow, you guys made it, 100 likes, thanks. Let's keep going. So when we got to solve this problem. This is fun. So what I have here is, I have to multiply stuff. Clear that away. So I have y minus b squared is equal to b minus a times x minus b. And what I'm really interested in is what is the y-intercept, okay? So that means I should write it in slope-intercept form. Y equals, there will be a b minus a times x. There's a minus b minus a times b, and there's a plus b squared. Let me pause for a second since it also ran into my head. What I just did here is I just took the b minus a times the x, that was this part, the b minus a times the minus b, that's this part, and it was minus b squared, so I added b squared to both sides. I got that. Now let's simplify. Y equals b minus a x. And what's this other stuff? I have a minus b squared plus ab plus b squared. Hooray! Cancel. Cancel. So what do I get for the y-intercept? The y-intercept is just ab. So this is explaining the question. This is amazing. This is just showing that if I took a normal y equals x squared parabola and I take a point and go up from on that side, another point, go up on that side, and you just look at where that intersects and get the y-intercept, that's the product of those two. This is neat. Let me tell you where I learned this first. I learned this first when I was long after school. It was when I went to the National Museum of Mathematics in New York City. The National Museum of Math, I've already talked about here. They have the square-wheeled tricycle, and they also happen to have this tic-tac-toe or 15 game you saw me talk about in this live stream. And they also have this exhibit. They have this thing. They call it the string product exhibit. That's just what they happen to call it. But it's just a huge parabola shape. And what you see is that where these things go across, that just tells you the product. You can go and find out how to multiply numbers just by drawing a string through that. This actually can give you a calculator, by the way. If you want to multiply two numbers, what you do is you just kind of measure. It's almost like with a ruler. You'd measure out the number, the distance like in inches or something going out that way. Measure out the number going that way. And imagine you can do this even with numbers with lots of random digits after the decimal point. If you just could make the numbers accurately as, measured out distances and measure out that distance. Then you just go up, and you connect across. And wherever it crosses there, that's the product. Really cool. Okay, well, in that case, I want to say we had a lot of fun today. Thank you very much, everyone, for asking lots of nifty questions. I learned something. I hope you guys did too. I also saw that we seem to be getting more people, which is making me happy. I also see that somehow it seems like a lot of people who join us tend to stay. And if that's the case, I'm also happy to see that. If you liked what you saw, please do tell more people. I don't know if you noticed, but if you go to the live stream website, what you've seen is that there's an announcement that we're soon going to have a collaboration with Math Counts. If you've ever heard of Math Counts is one of the most interesting competitions out there for middle school students in the United States. So if you saw that, it looks like next week, probably next week, Wednesday, Thursday, Friday, we're actually going to be using our live stream sessions to do some Math Counts problems, to actually talk over this year's chapter round. You'll hear more about that soon. Okay, great. Please do tell more people. We'll have a lot of fun. And as usual, I'll tell everyone, please stay safe. Please be responsible. Please do not play the tone generator into your headphones. Please do not cheat your friends with all the tricks that we've learned here. And please do not touch any light bulbs. See you next time.